Hello and welcome to another tutorial. In this tutorial I'm going to continue the discussion on sequences and series, and to recap, we discussed about sequences, and we said that if you consider a dense function f of x, which with x being a real valued function and f being a continuous function, we get a dense plot of the function. Now if we evaluate f only at integer or the integer numbers, could be positive or negative, we end up with a discrete sequence of numbers or values for f, and we said that we call this a sequence. And the convention is that instead of using f of n, we use f sub n or a sub n. Okay, so n here can only be an integer number, and we said that the sequence can be increasing or decreasing, or monotonically increasing and monotonically decreasing. And then we said that one important property of the sequences is the limit of the sequence as n tends to grow larger and larger. If the sequence approaches a specific number, we call that the limit of the number, and we can actually have a mathematical way of defining whether or not a sequence has a limit, but that's not the point here. And these are just two examples: 1 over n squared if n goes to infinity approaches 0, and 1 plus 1 over n to the power of n when n goes to infinity equals e, the Neper number. And we said that we can implement a sequence as a functional interface, as we did previously. And next we talked about one important class of sequences, which is recursive sequences. And we said that in a recursive sequence, each term is defined as a function of the previous terms. And for example, Fibonacci, each term is the previous term plus the second previous term, an minus 1 plus an minus 2. And this is an example of linear constant coefficients recursion, and these type of recursions have indeed closed form solutions. We can find them. Geometric sequence, each term is some constant number times the previous term. Factorial, each term is the index at that term times the previous term. So here n is not a constant number, this coefficient. So this is a nonlinear recursion. Okay. And then we said that initial conditions are required to uniquely determine the sequence at each given index. For example, for Fibonacci, and the initial conditions depend on how many terms, how many of the previous terms appear in the definition of the sequence. For example, in Fibonacci we have 2 of the previous terms, so we need 2 initial conditions, a1 and a2. Geometric sequence, 1 term only appears, so we only need 1 initial condition. Same as factorial, only 1 previous term appears, so 1 initial condition. And we said that it's easy to directly implement recursion in Java. Okay, we just implement the recursion in calling the method that evaluates but then we need to also take care of the initial condition, the check for the initial condition, or when the recursion ends. Now we said that recursive implementation in Java is typically expensive and costly, so if we can't find a closed form solution for the sequence, it's better to implement it via the closed form solution. And then we discussed the other important concept, which is a series. And series is by itself is a sequence, but that's a sequence that is constructed over the summation of another sequence, A. So A is also sometimes called the generating sequence, and S is called the series. Okay, and typically the initial index of the summation is fixed, and then the final end index is where the series is defined over, right? And we typically start from the initial index is either 0 or 1. That's the typical case. And then we said that in cases where evaluating the series, evaluating the generating sequence A is costly, is expensive in terms of computation, we can do caching, okay? But if it's easy to evaluate the generating sequence, caching doesn't offer any improvement and may even worsen the performance, as we saw in the last video, in the previous video. But in general, when we deal, if we deal with cases that we need to calculate these coefficients many times, then it's better to do the caching and save the coefficients. Because if I calculate S3, I need to calculate all the AIs from the initial index to 3, and then S4 from initial index to 4. But if I have already calculated the initial index to 3, I can just use them again. I don't need to recalculate them, unless recalculating is easier than caching. And the simple way to do caching is using a hash map. All right, a hash map pair of integer and double value. Integer is the index and double value is the result or the value of the sequence A. And then we said that series can also converge because this is a sequence, so we can also define a limit for this series. And if after some large n, the distance between the two terms of the sequence is less than a small value, we say that the series converges, and there is a convergence. And then the value of the limit is basically the value of the series, infinite sum. And then we said that if the generating sequence is monotonically increasing, this could in fact lead to a divergence. And the necessary condition was that for the generating sequence, the limit of the generating sequence must be 0 in order for the series to be able to converge. Doesn't guarantee convergence, but that's the necessary. So if the series converges, the limit of the generating sequence an must be 0. So that's one test to see if the series converges. We can find the limit of the generating sequence, and then we can implement a convergence test when one of the indices, here let's assume the upper index, the end index goes to infinity, okay? And then the convergence test is basically how to decide when to terminate the sequence, the sum, and whether or not the sequence of the sums converges or not. So in terms of testing for convergence, the question is what criterion should we use for convergence test, right? And the problem here is that we don't know the exact value of the limit. So exact here is the keyword, right? We don't know what the limit is. So if I know what the limit is, then I can decide how far the value of the sequence is from that limit. And that gives me a sense of the error that I have if just I terminate the sequence at some given index, all right? So because we don't know the exact value of the limit, then we have to define the error without this value. So, and if we have the exact value of the limit, the absolute error of the sequence when we terminate at some index is the estimate at index n. Let's say n is where we terminated minus the exact value. But if we don't have the exact value, what we can do as an alternative is to define an error sequence, okay? An error sequence is basically the current estimate where we want to truncate it minus the next estimate. So if these two are very close enough to each other, then we can confirm or assume that the sequence converges, okay? So, and this gives us a sequence for the absolute error of the sequence, each term relative to the next term, okay? Now similarly, the problem here is that maybe the limit is very large, and these terms are also very large. Let's say the limit is 10,000, and this is 10,020, and this is 10,022. Okay, so the problem is that the difference is still 2, and 2 could be a relatively large number. So when we're dealing with absolute error, we don't know what is the tolerance. Let's say eventually we want to truncate the series based on saying that, okay, the absolute error is less than something, but how do we come up with that something? That also depends on the magnitude of these estimates, right? 2, for example, 2 could be a large number, and let's say we want to have absolute error less than I don't know, 10 to the negative 4 or 5 or something. So a better case is relative error, and the relative error, again, if we have the exact limit, we define it as the exact absolute error divided by the exact value, which is the limit. Now obviously if the limit is 0, then we are in trouble. All right, so another way is to define a sequence of relative errors, which is the absolute error at position n, at index n, divided by the estimate at n. So this basically tells us how relative to the current estimate, how much the next estimate changes, right? So if it's 1%, it means the next estimate only changes less than 1%, and that could be a good condition for terminating the sequence and assuming that the series convergence. Okay. Now, if a sequence convergence, or let's better to say, if the series convergence, the absolute error must go to 0. That's these two are and the relative error goes to 0. The relative error goes to 0 because the absolute error goes to 0, because that's the definition of the limit, right? The limit is when the estimate minus the exact value is less than some number, some small number. But again, we can prove that if the series convergence, the sequence of absolute errors must go to 0, and the sequence of the relative errors also goes to 0. Okay. Now the problem here, one problem that we always have when we're dealing with numerical sequence, is the speed of convergence. All right, this is a key here, because that determines how fast we can get a good estimate, a reliable estimate of the limit. And there are numerical ways to accelerate the convergence of the sequence, but we're not going to talk about it here. All right, let's head to Eclipse and try to implement the convergence of series. So to recap, we implemented the sequence as a functional interface with only one function that evaluates the interface at a given integer. Here I changed the integer to long because long is 64-bit while integer is 32-bit. So we can go to larger integer numbers with long. Okay, and then we create a series class, has a generating sequence. All right, we implemented the cache, which is a hash map of integer double, and we set a flag do cache, and if it's false which is by default it is false, then we don't do caching, we just evaluate the sequence. And then here I added the double convergence tolerance. This is the tolerance we use for relative error. And then the max iteration, when we're doing a sum over infinite number of sequence, infinite number of indices, we should have a max iterations, right? Because eventually, even if this is not met after some time, some number of summations, it's better to just terminate it. So I put it by default 10,000, but we can change it. So the series class is defined by taking a generating sequence, and then if we want to sum over in the finite number of indices, we have a get value method that takes the initial index and the final index. But then here I implemented another method for only with initial index with implies infinite sum, right? We're summing from the initial index to infinity. Okay, so here I set the result to 0 initially and define temporary variable, and this temp is going to hold the value of the error, absolute error, which is basically the difference between Sn and Sn minus 1 is just the value of the sequence at that index, right? And k is the initial index, and I put it in a while loop while k is less than max iteration. So this is the first termination criterion. So we want to only sum over a finite number of indices. We don't want to solely rely on a tolerance for convergence. Okay, and in engineering, most of the sequences that we have, especially in physical problems, they usually converge relatively fast, so we don't end up with summing 10,000 terms, and that's a good thing. But so one thing here is to have the a stop condition based on the maximum times that we want to do the summation, and then at each sum we evaluate the sequence, put it in our temporary, and then add it to the result, which was initially 0. So the result is accumulating the sequence, accumulating Sn. Temp is basically just the value of An, right? A sub n and S sub. So result, and then next we check whether or not the sequence has converged, and if it not, then we increase the index and go back to the beginning of the while loop and try to add more terms. Okay, and then so what is this converged? Converged takes the error, which is the value of the sequence. Basically, if you recall, An is Sn minus Sn minus 1. Okay, so we take An and we take also Sn, and then we say that okay, let's print the absolute error, which is the magnitude of temp, and let's say that the tolerance for the absolute error is 1 10 to the negative 8, and then the relative error, which is the temp, which is the absolute error divided by the current value of Sn, the result, and tolerance is the convergence tolerance, which we set it to 10 to the negative 10. Okay, and then absolute error again is the magnitude of temp, the relative error is and we can even put these in the beginning, and then here we just put absolute error and we put relative error. Okay, and then we have to check for both the relative error and absolute error. So we said that sometimes relative error is better, but sometimes, especially if the terms of the sequence are small, it's better to have the check for the absolute error too. And if you also recall, I said that the necessary condition for the convergence of the Sn, the series, is that the limit of An, the generating sequence, which is our temporary or the absolute error, should go to 0. So we want to also make sure that this sequence goes to 0, An. Otherwise, the series doesn't converge, right? So checking for the absolute error is also necessary. So here I'm setting it to 10 to negative 8, and the tolerance for the relative error 10 to negative 10. All right, so this is how we can test for the convergence. Now let's head back and create a class to test this, test convergence, and I'm going to have a main method, and let's create a static method public static void test1, and in the main method I just run test1. Alright, so in the test1 I'm going to create a series s equals new series, and the generating sequence I'm going to use a lambda expression, and I'm going to have k times k, 1 over k squared. So the series here, our sequence is a sub n is 1 over n squared. Okay, and we know that this series converges, and this converges mathematically and converges, and the value for the convergence or the limit is pi squared over 6. We know that, we can mathematically prove it. So let's create the double value lim equals s dot get value, and I'm going to invoke the method with only one integer value or the line value, and from here I just put 1. So when you sum from 1 to infinity, so the series converges, and this sequence, the limit of the sequence is also 0. Okay, so what we are going to do is system.out.println and limit equals plus lim, and also a sysout exact equals plus math.py times math.py over 6. Alright, so let's run this. So we have max iteration reached, so the relative error never reaches 10 to the 10. Alright, but the limit is 1.6448 and the exact value is 1.6449. So up to 3 digits, decimal point digits, we are good. So that's a good convergence. So that's why I actually have this also. So at the end of checking for convergence, we can see if the k has reached the max iterations or not. If it has, then we say that okay, max iterations reached. Now we have to make a decision on the convergence or divergence, and then here I'm going to say that if the absolute value of temp, so basically I'm looking at the limit of the sequence, which is the absolute error. If it's more than 10, so remember this sequence an must approach 0. If it's more than 10 after all these iterations, 10,000 iterations, I'm going to call it divergence. And then if I'm going to just math.abs is less than 1e minus 5, I'm going to call it convergence. So maybe let's put this here, and I'm just add an else. Or else if let's say if this is greater than 10, we're going to call it divergence. And if something else, we're going to just say undetermined status for the series. All right. So we have convergence because even if the max iterations reached, we're calling it a convergence because the absolute error is very small. So we can confidently assume that it's a convergence. Now if I put, for example, k times k, so obviously this sequence diverges, and it's a divergence because max iterations reached. And note that the absolute error at the end is 10 to the 8. but the relative error is small, only 10 to the fourth. That's why the relative error may not be the best thing or the unique thing that determines convergence, unless we use a very large, very small relative error. That's why we should both test for the convergence of the absolute error. It has to converge to 0. If it converges to something else, the series doesn't converge. Okay? And so this is how we can determine. So we can use other tests. For example, let's test 2. And in test 2, I'm going to use another sequence. Let's say 1 plus 1 over n to the power of n, and we are going to check whether or not it converges. So we know that this series converges to this sequence converges to E, right? And therefore the series that uses an as its generating sequence must diverge, because the limit of an is not 0, it's E, the Neper number, which is 2.7, right? So let's see, the sequence is math.pav 1 plus 1 over k to the power of k, all right? And we're going to sum from 1, and we see what happens if we get a convergence or divergence. Now it says, okay, we have to run test 2. Says that undetermined status of series. So we summed up to 27168. And the reason is that the absolute error is still small. So we see that the sequence is converging to E. So let's also print E. Limit of an math.e. All right. 2.718, 2.7181459. So the sequence is converging because the absolute error is converging to the value of the sequence. But then the relative error is 1e to the negative 4. So max iteration is reached. And then in the series, what we said that, okay, we said that if the absolute error is less than this, we say that the series converges. We call it a convergence because at least we know that the limit of the an is 0, it's close to 0. But then if this is greater than 10, we call it a divergence. So 10 obviously is a large number. We can say 1e negative 2, for example, or something like that. And then we end up with a divergence. So it depends on how you implement this, and depends on the sequences. And based on that, you can write your own criteria for convergence and divergence, right? Okay, thank you for listening. I'll see you in the next video.